So this last bit I've creatively called other graphs. Basically, you just look at some HSC ones. So we see the sorts of things that have been asked in the past. So in 2003, they gave us a random graph. But by the way, if you had to sort of guess what the equation of that is, what would you be expecting? Yeah, it's going to be the reciprocal of a parabola. I would expect that's what it is. Well, the roots would have -1 and 1, because that's what created the asymptotes, things like that. So you could sort of use that if you wanted to, but let's see what they asked anyway. At this stage, it's just a random graph. And they've asked us for the reciprocal. Well, if in that last one I've just gone, oh, hang on, I'm expecting some sort of parabola. Mind you, when I draw mine, well, it's a little bit dodgy. Let's see what we can do with our reciprocal. What did we say about the reciprocal? Well, it's a good idea if I know where 1 is. So on the scale that they've given me, I've placed 1. Turn the asymptotes upside down. We get the x-intercepts sort of. So there'll be point discontinuities. Turn -1 upside down, you still get -1. The original graph doesn't have 1 anywhere, so I can't turn that upside down. I can turn the 2 upside down and get a half. And that's pretty much all I really need now. It's sort of a parabola. It's an upside down U shape anyway. There we go. Next one was quite interesting. It combined 2 ideas together. The superpositioning, or the adding the 2 graphs, along with one of them being the absolute value. So we're going to add our function x graph with the absolute value of function x. Now, what will happen?
Oh, yeah, exactly.
No, that's not the answer. That's the absolute value of function x. So that's what I'm adding together. So in between the 2 asymptotes, that's easy, because it's just going to be twice what I've got there. So all right, that'll go to 4 and we'll get some sort of U shape there. But here's where people made the mistake on the outside. Because what they said was, I won't draw anything else now, because the other 2 will just cancel out.
Wait, no.
No, exactly, no. They don't cancel out, they add together to give 0. So actually, you have the point discontinuity at the asymptote there, but you'd have just the x-axis going either way. Yeah. You can see how easy that mistake would be to make, and sure enough, if I remember correctly, that particular year, a lot of people did make that mistake. Okay, let's square function x squared. Okay, well, if I square 2, I'll get 4. So again, inside the 2 asymptotes, I'm just going to get some sort of U shape. Every one of those y values is going to be squared. Well, the bit that's below the x-axis is going to become positive, of course. And it'll be a little bit steeper than the original one because I'm squaring it. That's pretty much it, really. So there's our graph, function x squared. Now, here's the more interesting type one. So this is a little bit different. It's what we call a composite graph, where we combine it with some other function. In this case, an exponential function. What I like to do is to the side, just to remind myself what's going to happen. So the basic curve here is the exponential. So we're going to go e to the power of function x. But then just to remind myself, I label the x-axis as function x, and then of course the y-axis is e to the function x. So in other words, I'm substituting in the y values of this curve into the exponential graph. So I look for some key points now. All right, what can we do? Well, the y-intercept if I substitute that in, I'll end up with, so function value is 2. If I was to substitute 2 into that one, I'd get e squared. So I know that's going to be e squared. Now, at this stage, we have the original graph has a horizontal asymptote at a function value of 0. Therefore, if I go to my graph, what happens at 0? Well, e to the power of 0 is 1. So the horizontal asymptote will move to y equals 1. So let's plot some of that in. The derivative, that's useful to find because it can tell me about stationary points, and we can see that the original stationary point at that x value, it'll still be a stationary point because f dash x is 0. E to the function x can never equal 0, so there aren't going to be any new stationary points. And again, inside there, we'll get some sort of U shape because basically we're going to be subbing in bigger and bigger and bigger values. Well, what happens with our exponential when we substitute in bigger and bigger and bigger values? The curve goes up. Now, the x-axis there. If you have a look at our original graph, what's happening at the asymptote? Well, it's approaching infinity or minus infinity. Well, this is where we're going to look at it from the left-hand side and the right-hand side. From the left-hand side, it's approaching positive infinity. So the new graph is approaching e to the positive infinity. So yes, it's getting really big. But coming from the right-hand side, it's approaching minus infinity. And e to the power of minus infinity, well, that's going towards 0. So that's why I know I'm going to have a point discontinuity at these 2 points. And there's the horizontal asymptote. So the question now is, what happens? Now you haven't got this in your notes, whether you want to write this down or not, I guess up to you. But this is the thought process. What's going to happen at that x-intercept? It might come in and go steep like that. And that's probably what most people would draw. Okay? Or, it's possible it could do that. Right? So it could go asymptotic, inflect, and come in. So we need to work out, is it going to come in steep or is it going to come in shallow? Well, the derivative is going to tell me that. So remember the derivative, y dash f dash x e to the function x. Okay? So we're looking at the positive side. We want to know what's happening when we approach it from the positive side of 1. Well, we know that f dash 1, so we're saying the slope of the curve at 1 as it's approaching from the positive side. Well, if you look at the original graph, that's approaching infinity. It's approaching a vertical slope. E to the function 1, well, we already talked about that one. That's approaching 0. So the question is, what's going to happen when we multiply these two things together? Infinity times naught, or if you like, 1 on 0 times 0. It's tempting to say, oh, the zeros cancel, and we get, well, we can't do that. This is where we use the idea of dominance. And just like we talked about with drawing a graph, you multiply two functions together, the exponential will dominate. So therefore, it'll approach 0. So therefore, it's actually the shallow one we want, not the steep one. And so, it got a little bit bumpy, but it's going to do that sort of turning point there. It'll inflect. So most people would have just done the concave down one. Okay, 2002. 2002. So again, here's random graph. Can't really guess what this one is. Is it a cubic? Probably not. But they've given us some points on it, which is good, so we can locate where 1 is and -1, things like that. So the first one, again, they've asked us to do the standard reciprocal. So let's do the reciprocal. Those x-intercepts will become vertical asymptotes. We know that. Well, -1, turn that upside down, we'll get -1. And +1, turn that upside down, we'll get +1. What are the other sorts of things we saw about the reciprocal? Whenever the original one's increasing, this one will be decreasing, and vice versa. I can work out what regions we're in based on above and below, turning it upside down. So it looks like we'll end up with something like that. Because remember, the other thing we knew, well, the stationary point was going to remain as a stationary point, things like that. So there's our red curve. So that would be our reciprocal. Y squared equals function x, which is normally quite an exciting graph to draw. But for this one, it's a little bit boring. Because what do we know? You can't find the square root of a negative number. Oh, okay. So that's what we're finding the square root of. But there is a trick to this one, a little twist in it. In that, there. That point at the origin still exists. So you end up with this single point at the origin. Now, as for the other bit, well, it looks to me like it's going to be a nice little vertical tangent there. It's cutting through like a straight line. So, something like that. There's our graph. Almost, because what haven't I done? Yes, they haven't asked for y equals the square root. They've asked for y squared equals function x. So, trust me, that is vertical there. That bump is purely your imagination. Okay. Oh, here we go. Absolute value of function, absolute value x. Remember, you substitute the x in first. So the first thing we do is function absolute value x. Because we've got to sub into that function first before we then take the absolute value. So function absolute value x, that was the one where we said goodbye to the left-hand side. You can wave with me if you like. Then whatever's on the right is reflected on the left. So that's function absolute value x. So now to get absolute value of function absolute value x, whatever is below is reflected above. Right. Okay, so this time, log of function x. So again, I'm going to draw myself a diagram over here. My log curve would do that. So my x-axis is function x, and this is log function x. So let's have a look at our log curve. And I heard someone say it, logs of negative numbers, we don't do that. So again, all of that bit below is going to disappear. In this case, the origin will as well, because we don't have log of 0. So all right, goodbye. Now, is it a point discontinuity? Is it an asymptote? Probably an asymptote, because if you look at our log curve, we get an asymptote. It sort of seems logical. But let's see what happens. Well, log of 1 is 0. So I know that's going to be an x-intercept. Well, what happens on the left-hand side of that? If I go back to my log curve, when I'm substituting in values between 0 and 1, I get negative. So now I'm looking at the original graph. Well, it's just increasing like numbers normally do. So we're probably just going to get a log curve. So we'll just get something like that. So, Cambridge, 8H.